Perseverance had just performed the most impressive Mars landing of all time. With its high-definition video of the parachute deploying and the sky crane's breathtaking footage of the rover's final descent onto Martian soil, it captivated and astonished people from every corner of the world. Engineers, scientists, and ordinary viewers alike watched in stunned silence as humanity's latest emissary touched down on another planet with a precision and flair that had never been seen before. But Perseverance isn't just a spectacle of engineering. Its primary purpose is far grander and more profound than any technical achievement. It exists to help pave the way toward answering one of the most enduring and tantalizing mysteries of our time. Before we begin, there's something I need to tell you. There's been a lot of weird stuff going on in space lately, so subscribe to this channel right now and I'll tell you even more secrets of the universe. In the comments below, tell us what you think of all this. Does life exist elsewhere in our solar system? For the past year or so, it has been the central mission of the Perseverance rover to search for actual evidence of ancient life on Mars and to prepare carefully selected samples to be brought back to Earth, where they can be rigorously and properly analyzed by scientists using laboratory equipment far more powerful than anything that could ever be carried across interplanetary space. So, what exactly has it seen, discovered, and done so far? Join us today as we continue our deep dive into the Perseverance mission and find out whether we are any closer to discovering signs of ancient fossilized life on the red planet. As the rover powered on its cameras and took in its surroundings for the very first time, it found itself staring out across the red, arid, and profoundly solitary landscape that we have come to expect from Mars. The terrain stretching out around it was mostly flat, though interspersed here and there with rocky outcroppings that jutted up from the dusty ground like the worn remnants of a world that had once been very different. This setting was entirely intentional. Scientists had deliberately chosen to bring Perseverance to a place where its 6 wheels could transport it with relative freedom and where it would be positioned within reach of sites offering particular scientific interest and geological richness. To that end, they had selected Jezero Crater as the rover's destination. Roughly 45 kilometers wide and located just north of Mars's equator, Jezero has existed as a feature of the Martian surface for at least 3.5 billion years. What makes it especially compelling is the clear geological evidence of ancient river deltas, sedimentary fan-shaped formations that could only have been deposited by flowing water billions of years ago. Where there was once water, the thinking goes, there may once have been life. Jezero, in that sense, seemed like an exceptionally promising place to begin the search. The kind of life scientists are looking for would likely have been humble by any measure. Such organisms may only have reached the level of simple bacterial life forms, single-celled and microscopic, leaving behind traces so faint and so small that identifying them requires extraordinary care and patience. The clues to their existence might be similarly tiny, making this search all the more challenging and exacting. Scientists would be on the lookout for any formations or structures preserved within the rock that could not reasonably be explained by purely geological processes. Unusual chemical signatures, particular mineral deposits, or morphological features in ancient sediment could all offer tantalizing hints or even definitive proof of ancient Martian microbial life having once existed there. Thanks to the outcroppings of rock that surround the crater, Perseverance would be able to collect samples from many different geological periods without needing to undertake major drilling operations. These exposed layers of rock act like pages of a history book, each stratum representing a different chapter in Mars' deep past, allowing scientists to piece together the geological story of Jezero Crater and build a clearer picture of which locations and which time periods might have been most hospitable to life. You might reasonably assume that Perseverance would have been on the move almost immediately after landing, eager and ready to begin the scientific mission it had been built for. With so much to explore and so many samples potentially waiting to be found, there was certainly no shortage of opportunity to get started. However, you would be wrong. Despite touching down on Mars in February, it wasn't until nearly 5 months later that Perseverance made any serious effort to leave its landing site and begin its journey across the crater floor. And this delay wasn't simply the result of scientists taking their time to carefully test every single piece of scientific equipment and its software, checking methodically to make sure everything was working smoothly under the harsh conditions of the Martian environment. Though that too was certainly part of it. The real reason for the delay was something rather more unexpected and, in its own way, quite extraordinary. You see, Perseverance was not alone when it landed. In fact, it may surprise you to learn that in a rather poetic sense, You might say it had arrived on Mars pregnant, cradled gently within Perseverance's undercarriage, sheltered beneath a protective dust shield from the biting Martian winds and the thin, freezing atmosphere. The rover had secretly carried with it a second, smaller passenger across hundreds of millions of kilometers of deep space. A significant portion of those first months on Mars was devoted to carefully and methodically helping bring that second passenger into the world. This hidden companion was to serve as both a fellow explorer and a remarkable technological demonstration, a proof of concept for something that had never been attempted on another planet before. The smaller robot was not a rover. It had no wheels, no arms, and no way to roll across the rocky terrain. Its name was Ingenuity, and it was humanity's first ever attempt at powered, controlled flight on Mars. A helicopter, impossibly delicate and feather-light, preparing to lift off into an atmosphere barely 1% as dense as Earth's, and in doing so, change what we believed was possible far from home. After performing several tests on Perseverance's own software and hardware, scientists turned their attention to this smaller 1.8 kilogram drone. The atmosphere on Mars is approximately 100 times thinner than Earth's, which made it deeply uncertain whether a helicopter's spinning blades would generate meaningful lift at all. With so little air to push against, displacing enough of it to overcome gravity seemed like a genuine engineering challenge rather than a given. Ingenuity was made incredibly lightweight, precisely to compensate for this hostile environment, and its twin counter-rotating rotors were engineered to spin at speeds exceeding 2,700 revolutions per minute, far faster than any helicopter blade needs to spin here on Earth. Its scientific payload was deliberately minimal, consisting essentially of a single camera, but that camera would prove invaluable in a very practical sense, helping Perseverance identify the safest and most efficient routes through the potentially treacherous and boulder-strewn Martian terrain below. So, on the 21st of March, nearly a full month after landing, the birthing process began in earnest. Perseverance started by carefully removing its protective dust shield, the panel that had kept Ingenuity cocooned and clean during the long interplanetary journey, finally allowing the little drone to taste the thin, cold Martian air for the very first time. Mechanical birthing is a slow and painstaking process, however, with scientists constantly monitoring every single piece of incoming data to verify that each component was functioning exactly as it should. Teams on Earth scrutinized telemetry readings with tremendous care, knowing that any overlooked anomaly could spell the end of the mission before it had truly started. It wasn't until the 3rd of April that Perseverance finally lowered Ingenuity onto the hard, rust-colored Martian soil and allowed it to face its first cold night entirely alone on the surface. Temperatures on Mars regularly plunged to lows of around minus 100 degrees Celsius, so surviving outside the warm, protective embrace of Perseverance's internal heaters was no small feat whatsoever. The fact that Ingenuity made it through that first brutal night with all its systems intact was cause for genuine relief among the engineering teams. Scientists were quietly delighted that this critical phase of the mission had unfolded without incident. During this careful deployment stage, Perseverance looked on like a proud parent as Ingenuity began to take its first tentative wobbling steps toward independence. Although just like any proud parent, Perseverance couldn't resist pausing to take a selfie or two to share with its many followers back on Earth. The images captured during this period, showing the rover and the tiny drone side by side on the ancient Martian landscape, became some of the most striking and widely shared photographs of the entire mission. Ingenuity's first flights did not go completely without a hitch. After spending time carefully testing its rotors at gradually increasing speeds, the drone did run into some software issues that genuinely worried the engineers who had devoted years of their careers to building it. A timing problem in the command sequence threatened to delay the historic first flight, and the team had to work quickly to develop and upload a software patch across the vast distance separating Earth from Mars. However, by the 19th of April, the problem had been resolved, and Perseverance was stationed and ready to record as the solar-powered drone attempted the first ever controlled, powered flight on another planet in human history. The entire flight sequence was carried out autonomously, with no real-time human guidance, because the signal delay between Earth and Mars at that time would have made remote piloting completely impractical. Commands were uploaded in advance, and then the team could do nothing but wait and trust the software they had written. There were a great many unknowns hanging over the attempt. Mars has significantly lighter gravity than Earth, roughly 38% of what we experience here, and its atmosphere is so thin that the two factors combined created a flight environment with no real equivalent anywhere on our planet. Testing the rotor system on Earth, even in specially constructed low-pressure chambers, could only approximate the real conditions. Truly replicating lower gravity on Earth in a meaningful way remains a stubborn engineering challenge, meaning that a degree of uncertainty was simply unavoidable. But fortunately, and with remarkable smoothness that seemed almost anticlimactic given the years of effort behind it, Ingenuity rose steadily to an altitude of 3 meters and hovered there for 39.1 seconds, performing exactly as planned before descending gently back to the surface. The mission team erupted with celebration. Scientists were deeply excited to see a technology demonstration that had been proposed just 6 years earlier finally prove itself a resounding success in the most demanding environment imaginable. Ingenuity had never been expected to last long on Mars. It was conceived and presented to the world as a short-lived technology demonstration, something to establish proof of concept and then quietly expire. But it kept going and going, flying further and reaching higher altitudes with each successive flight than anyone had anticipated. It didn't crash, didn't break down, and over time gradually transformed into something far more useful than anyone had originally dared hope. It became a genuine scout for Perseverance, ranging ahead to identify good routes for the rover to travel, to map the ground in detail, and to seek out points of scientific interest too small and too fine-grained for orbiting satellites to detect from high above. Ingenuity evolved from a disposable technology experiment at the very beginning of the mission into a trusted and valuable companion for the Perseverance rover, fundamentally changing how the mission operated on the ground. But what about Perseverance itself during all of this? The rover was far from idle while Ingenuity was being carefully deployed and tested. Perseverance used the waiting period productively, putting many of its own instruments through their paces in the real Martian environment for the very first time. Among its more surprising pieces of equipment was a microphone, and scientists were hopeful it would capture the first true audio recording ever made from the surface of Mars. Soon after landing, Perseverance was able to do exactly that, delivering to humanity its very first impression of what the wind on Mars actually sounds like. The recording is sparse, haunting, and utterly alien, somehow deepening the already profound sense of desolation that the barren Martian landscape conveys. It is worth noting that earlier audio-style files captured by missions like InSight were not recorded by a microphone at all. They were instead produced by converting into sound the physical vibrations that Martian wind created as it moved across InSight's solar panels. The difference between those reconstructed sounds and a true microphone recording is striking and well worth exploring. Perseverance also spent this early period driving short distances to test its motors and wheel systems under real Martian conditions, capturing sweeping panoramas of the surrounding landscape, and accomplishing one achievement whose significance quietly dwarfs many of the mission's more visually dramatic moments. Using its MOXIE instrument, the Mars Oxygen In Situ Resource Utilization Experiment, Perseverance successfully extracted breathable oxygen directly from the carbon dioxide that makes up the overwhelming bulk of Mars's thin atmosphere. This was a first, and it is more profound than it might initially appear. For future human explorers or colonists hoping one day to live and work on Mars, the ability to produce oxygen locally rather than hauling it all the way from Earth would be transformative. But oxygen has another essential use that often goes unmentioned: rocket fuel. Any crewed mission to Mars will eventually need to leave, and escaping even Mars's lighter gravitational pull still demands an enormous amount of propellant, somewhere in the range of 30 to 45 metric tons, depending on the mass of the spacecraft and its payload. Manufacturing that propellant on Mars itself, rather than carrying it from Earth, could be the difference between a mission that is logistically possible and one that simply is not. Leaving Earth is already one of the most technically demanding feats humanity has ever attempted, and the challenge grows considerably harder when you factor in the need to carry not just the fuel required to get somewhere, but all the fuel you will need to make the trip home again. Every kilogram of propellant loaded onto a spacecraft adds weight, which in turn demands even more fuel to lift it off the ground, creating a deeply frustrating engineering spiral that has constrained the ambitions of mission planners for decades. Knowing then that we might be able to manufacture most or all of that return fuel directly on another planet using resources already present in the local environment transforms the entire equation and makes crude interplanetary travel far more practically feasible than it would otherwise be. MOXIE, which stands for the Mars Oxygen In Situ Resource Utilization Experiment, was designed to test exactly this idea on the Martian surface. The device works by drawing in the thin Martian atmosphere, which is composed of roughly 95% carbon dioxide, and running it through a process called solid oxide electrolysis. At extremely high temperatures, the instrument splits those carbon dioxide molecules apart, separating the carbon from the oxygen and allowing purified oxygen gas to be collected. In its early trials, MOXIE managed to produce approximately 10 grams of oxygen in the space of 1 hour. That might sound underwhelming at first, barely enough to sustain a small campfire, but the figure becomes far more meaningful when you consider the context. MOXIE is, after all, only a prototype, a compact proof-of-concept device roughly the size of a car battery, designed not to power a crewed mission, but simply to demonstrate that the underlying chemistry works reliably in actual Martian conditions. Scaling the technology up to something genuinely useful for human exploration would require a version perhaps 100 times larger, capable of generating oxygen in quantities sufficient both for astronauts to breathe and, crucially, to serve as the oxidizer component in rocket propellant for a return launch. That is an enormous engineering leap, but the most important step has already been taken. The principle has been validated in the field, and just knowing that it works in the cold, low-pressure reality of the Martian surface rather than merely in a laboratory on Earth is a genuinely exciting milestone in the long road toward human spaceflight beyond our own world. But fascinating as all of these developments were, there remained one overriding purpose that had brought Perseverance to Mars in the first place, a question so profound and so consequential that it dwarfs almost every other scientific inquiry humanity has ever pursued. The rover had come here to discover whether there was ever life on Mars. Not necessarily life today, in the planet's current frozen and irradiated state, but life in the deep past, billions of years ago when Mars was warmer, wetter, and far more hospitable than the barren wilderness it has since become. That was the mission's beating heart, and everything else, the technology demonstrations, the helicopter flights, the atmospheric experiments, was in service of that singular goal. During the extended period of early operations and system checkouts, scientists back on Earth were busily plotting the best possible route for Perseverance to take across the crater floor. Although the landing had been one of the most accurate Mars touchdowns NASA had ever achieved, guided by the sophisticated terrain relative navigation system that had steered the rover through its final descent, Perseverance had still come to rest many days of driving from the geological features scientists were most eager to examine. At the edge of a region known as South Seta stood dramatic outcroppings of rock rising up to 40 meters tall, ancient formations that had been shaped by the lake that once filled what is now Jezero Crater, and which scientists suspected might harbor chemical or even physical traces of past microbial life preserved within their layered structure. The problem was getting there. Between Perseverance's landing site and South Seta lay a treacherous dune field, wide swaths of loose, deep sand that shift and settle in ways that could trap a rover's wheels beyond any hope of recovery. The fate of NASA's Spirit rover, which became permanently embedded in soft Martian soil in 2009, was a cautionary tale that no mission team wanted to repeat. Crossing the dune field directly was simply not an option. Scientists therefore faced a navigational decision with real consequences for the mission's scientific return. The rover could travel anti-clockwise around the edge of the crater, a more direct path that would deliver Perseverance to the South Seta outcroppings more quickly, or it could head clockwise, a longer and more time-consuming route, but one that would carry the rover past a greater variety of interesting rock exposures, offering additional opportunities for sampling and observation along the way. Both options had genuine merits, and the choice reflected a fundamental tension that runs through all of space exploration, the constant negotiation between speed and thoroughness, between reaching the headline destination and doing the maximum amount of science along the journey. In the end, as is so often the case when mission planners are working within the hard constraints of time, power, and mechanical wear, it came down to efficiency. Scientists chose the clockwise route, reasoning that Perseverance should extract as much scientific value as possible from confirm every kilometer it traveled, rather than rushing past potentially significant sites in the interest of reaching the main target sooner. Every rock formation, every sedimentary layer, every patch of ground that bore the hallmarks of ancient water activity was a potential clue in the search for past life, and passing them by without investigation would have been a waste of an opportunity that might never come again. With the route decided and all systems confirmed healthy, Perseverance was finally given the go-ahead. On the 1st of June, almost 5 months after first touching down on the red planet, the rover's 6 aluminum wheels ground into motion, and Perseverance rolled away from the relative safety and familiarity of its landing site, setting out across the ancient crater floor on its primary mission. Its objective was to seek out and collect core rock samples from geological locations where conditions might once have been suitable for life to gain a foothold, preserving those samples in sealed titanium tubes for eventual return to Earth, where the full analytical power of terrestrial laboratories could be brought to bear on them. The search for evidence of alien life, perhaps the most momentous scientific investigation in human history, could now begin in earnest. And following along overhead, scouting the terrain and relaying information that would help guide the rover's path, was Ingenuity, the small helicopter that had already rewritten the history books as the first powered aircraft ever to fly on another world, accompanying Perseverance like a loyal and remarkably capable companion into the Martian unknown. That's all for today. If you like space stories and want to stay up to date with new episodes, subscribe to this channel and turn on notifications. See you in the next podcast.